And we started last time talking about when good programs go bad. And we talked about two ways of handling these: return codes and exceptions. What were some of the trade-offs associated with each of these? What are good and bad sides of exceptions?
A lot of bookkeeping of exceptions.
Okay, bookkeeping, which leads to computational performance overhead. So that's important. Other things?
Makes it hard to find like mistakes and stuff in your code.
Yeah, making it hard to find mistakes. You're not sure where it's bombing out. Another thing?
Abstraction.
Yeah, there's violations of abstraction often. A calls B, B calls C. Unbeknownst to A from B's interface, C throws an exception. Now A has to get involved, all tangled up in what C is doing and how to clean up after C. And there's ways of taking C's exceptions and putting them into B's interface so that when you look at this method in B, it says clearly it can throw these exceptions. But in Java, for runtime exceptions, that's not enforced. And so you can get this situation where a runtime exception is signaled down here that A doesn't even know to expect. Doesn't even know B is using C. And suddenly, it comes up. So good. Exceptions are a powerful tool. They're a tool that allows us to handle exceptional situations, but they have some drawbacks. Another one of them being code scattering. There's kind of code scattered among the main block, the exception handler block, the finally block, the try, exception handler, finally. There's different code in different places, and it's sometimes a little bit overwhelming. How about return codes? What's good, what's bad, and what's ugly about them?
They're not enforced.
Okay, they're not enforced. There's no compiler type checking for them. It's not recognizing this can return a value that's distinguished to mean it failed, or it failed for this reason, that we have no value returned from the find, or from no value returned by lookup in this dictionary or something like that. And so we return a magic number like -1, but it can just be blown away. The compiler isn't saying, hey, you got to handle this, because it doesn't know -1 is different from +1. It doesn't know there's something special that needs to be dealt with. So that's one of the biggest shortcomings of return values. What's a positive side of return values?
They're very lightweight.
Sorry?
They're very lightweight.
They're very lightweight. They don't impose significant performance overhead. Another thing? Well, they can be processed kind of in the course of normal operation. And after all, they're a value. They're not a separate sort of thing like exceptions, which has its own parallel hierarchy that you got to handle. They're a value, and they get passed around as a value, and they can be processed as a value and handled, with if-else type reasoning or what have you, that can be mapped to various conditions. They're not a sort of special sort of thing that, like exceptions are, that requires a very different sort of handling. Return codes are something we know how to deal with quite well. What's another big issue with return codes, though, that we haven't heard? Particularly when you get into code bases put together by multiple people. Inconsistencies in, what different return codes mean. Is 0 good or is it bad? Is that a sign that it succeeded or failed? Or, what does -1 mean compared to -2? And, we can put in place documentation for conventions of these things, but it depends on convention. It depends on us having good good coordination, good shared documentation, and shared expectations. And sometimes things fall through the cracks. The case was mentioned back there of, two developers working on a code base, and each of them had a different convention for how to encode success, and both are reasonable, but they're different, and they don't play well together. Okay? So exceptions and return codes. Very important. When do we use return codes compared to exceptions? When do we not use exceptions?
It's stuff that occurs very frequently.
Very frequently. Things that are expected to occur. End of file. This key wasn't found in the dictionary or what have you. Things that are occurring frequently enough in the course of things that you expect them to happen at some point or another in perfectly reasonable operation. You don't use exceptions there, amongst other things, because they're really heavy weight when it fires. You got to roll things back. Another problem with exceptions that we had mentioned is resource handling, right? We're kind of spoiled these days a little bit. I don't say that in a bad way. It's good. We're kind of spoiled by memory cleanup which used to be the bane. 20 years ago, if I had been here speaking with you, one of the things I really want to school you on is how to manage the allocation of your memory to avoid memory leaks, to avoid loose pointer exceptions, etc. But these days, a lot of that's taken care of for us. But there are a lot of resources that need to often be freed up or dealt with by exceptions when they bomb out. Things like file handles, things like database connections. These parts of transaction management, etc. And so exceptions, have to deal with these resource dependencies in big ways. And exceptions are used for exceptional conditions. Conditions we don't expect to happen, but if they do happen, it's an unusual condition. We gotta handle it. Okay. So unexpected, rare events. Return codes are commonly used for common expected events. And assertions, as we'll see, are used for a different class of thing. What are assertions used for?
Assumptions?
Yeah. Whose assumptions?
Developer.
Developers' assumptions. Not user assumptions, developer assumptions. Okay? The idea here is to alert programmer to misplaced assumptions. If my assumptions were violated, maybe because of a mistake I've made in my reasoning, maybe because of an evolution of the code base that occurred after I put that reasoning in there, maybe because someone else who's a client to my code has violated my preconditions, passed me something that I've said I don't allow, but they've passed it to me. It's a developer mistake. It's a developer oversight or inconsistency or what have you. And I noted that it documents assumptions. It says what I'm assuming and checks it at the same time. It operationally documents it, meaning it documents it in the course of actually confirming it or checking it. And it reduces the likelihood an error will slip through. It helps debugging, because often these these assertions can catch things when things are off during debugging, and it brings it. The problem is discovered. A failure occurs much closer to the underlying fault. Let me make that distinction. I want to make sure, I've mentioned it before, but I want to make sure that's sunk in. Ladies and gentlemen, we have faults in our programs. These are the very particular errors that are in the programs. And those give rise to failures. These are kind of observed pathologies, observed cases where the program does not operate properly. It may be an error message. It may be some corrupt data. It may be a crash. It may be a hang of the program. It freezes. It may be it just performs extremely slowly, but we have failures of various sorts. Now, faults are often much harder to observe. What are we doing in debugging? What are we trying to do in debugging in this language?
Trying to find the source.
Yeah, so we're going from a failure, an observation of a failure, as might have been identified by testing, and we're going back to remove the fault, right? We're trying to locate the fault. And that process of debugging can often take a long time. How many people in here have spent more than 2 hours before debugging a defect? Okay, so you know what I mean. How many people here have spent more than 2 days? Okay, I'm probably in that group, back with Heisenbugs and C-pointer errors and so on. 2 days is about the limit. As a professional developer, I spent chasing it out. It may have been a day and a half. But yeah, it took a long time. Ladies and gentlemen, this is a real art and science. It's a real art and science. And if we have some time at the end of class, not today, the end of the term, I'd actually really like to talk about this, because there's a factor of 10 difference in terms of how people can zero in on the same bug. And it's not because one is, Einstein impersonated or something. You don't need that frizzy hair and so on. It's because they have a principled way of going about it. It's a methodology to go about debugging. And you can do it 10 times. Think about that. From 10 hours to 1. This is documented. 10 times difference in debugging speeds. So debugging is a painful process, and we're going back to faults. Now, the closer the failure can occur to the fault, the more proximate in time, the more quickly the program discovers something's off, the quicker debugging can take place, because less has gone on. Between then, you're closer to the mistake. You see, oh, it's during this operation that it first happens, rather than 5 minutes later it crashes. So assertions are kind of along this way, and assertions allow failures to occur much quicker, right? Instead of that null pointer causing a crash 5 minutes from now, it's caught, milliseconds after it originates. And that can let you bring back. Do you appreciate that issue? Does that make sense? An assertion, your code has lots and lots of assertions looking for things that are off. It's hard to slip through that net. It's hard for a bug to slip through that net as easily. You understand that? Okay. It's an important component. Now, I want to bring an additional factor to bear, though, just because it's important to connect these concepts. And now we're talking about faults and failures, and where assertions play a role. Where does peer review play in all this? We're talking about testing. And where does testing play in this? What is testing doing in this picture? Where does testing play a role?
Trying to get the system to fail.
Yeah. So testing helps us identify failures. Testing helps us find the failures, right? And then, having been found, we engage in debugging to find the underlying faults. Testing reveals failures that are merely latent, that would happen, we just haven't stumbled across them yet, right? This is why we do code coverage testing. We want to make sure that at least we've reached a certain point in this system before. We've reached this part in the code, because otherwise there may be a failure there we don't recognize. So testing helps us find failures, and then we go and debug, right? We go and we trace them down. We make sure they're a real failure, they're current, they're not a duplicate, make sure that they are well described, and then we try to reproduce it, and we try to debug it, and we get to the faults. Where does peer review figure in this?
It finds the faults.
Yes, peer review, ladies and gentlemen. That is the key thing. Peer review, pure faults. No, it doesn't well, sometimes it identifies pure faults, but but that's not its goal. It identifies the underlying faults. Sometimes there are some faults that come out. We've had a couple times in this class or its graduate variant where peer reviews have gone sideways in bad ways. And the most common pathology is that the person responsible for the item being reviewed gets all defensive about it and starts shouting and being very angry about the critiques of their code, rather than viewing it as, okay, how can we work together to make this even better? And that can identify peer faults. So peer reviews here find faults directly. You're studying the code base, or you're studying an aspect of the design, and you spot a problem. Wait a minute, it doesn't handle this case. Wait a minute, this, when the memory is exhausted, there's not a handler for that. And it can allow you to zoom in on the faults quicker. So peer review actually can allow you to cut out debugging time and identify the underlying faults directly. This is one of the reasons it's so powerful as a tool. We study it, we find the underlying problem through analysis, rather than trying to find a failure which indicates it and working back to debugging. And assertions can help in peer review, actually, too. They can, if there's assertions in there, why do they help in peer review? Give me one way it helps in peer review. If this code has lots of assertions in it, why does it help?
You can see all the assumptions that
You can see all the assumptions the person made. It really helps the reviewers understand, oh, okay, this is what this person's assuming. That's why this code has this feature. That's why they're not handling this case. It's an assertion. It's something that they thought through and realized this can't be the case. And if that assertion isn't failing, it gives some confidence that, yeah, this is true. And after that assertion, below it in the code, you can assume that, okay, it's reached this point, that thing must be true. So, it'll help the reasoning about that. So assertions help peer review, and they help testing by showing failures. Ladies and gentlemen, assertions in a word are awesome. And they're very little cost. They're very, very good things. I don't know that I'd say that this diagram is awesome, but I'm going to take a photo of it and incorporate it in the slides so that I can share it with you. Unfortunately, it's okay. Hey, come on, focus, guy. Good enough. Okay. This angle is somehow better. Hey, there we go. Ooh. You ever notice Android doesn't quite focus properly sometimes, the camera app. Okay, so they reduce debugging time and they help improve the thoroughness of tests. Okay, we talked about ways of doing offensive programming. This is not merely about defensive programming. This is about getting your program to fail if it has a bug. The goal of the assertion is to fail early. Why fail early? To find failures closer to the underlying fault so we can debug them more easily. Okay. So documents assumptions, reduce the likelihood it will slip through, reduces debugging time, etc. Here's some common errors that are caught. So, ladies and gentlemen, man, if you're creating, these contracts for your code, checking preconditions and postconditions is a freebie. It's a freebie. You check the preconditions for your method, and you check the postconditions, the things that are supposed to be the case at the end. It's supposed to be returning, and it's the first index where there's a duplicate from earlier. Okay, well, you could check that it's a duplicate in the assertion, Check to make sure the thing being returned, in fact, is the square root of the thing passed in by squaring it and seeing if it's close. Take a look if this is supposed to be the first empty point in the tree. To insert something in a node, check to see if it's free. Make sure the thing you're returning is not null. There's all these things you can do. It doesn't guarantee it's working perfectly in most cases. but it will help rule out whole classes of errors, right? Sometimes we check very basic things. Okay, so maybe this is a few years ago, before the city of Saskatoon had one. Students in this class created a transit app about taking buses across the city. So you could say, I want to go from University to the airport, and so it would figure out the routes that they could take, and their code had a lot of thinking that went into it. But just a few extra assertions could have spotted a lot of things. For example, their code had a pathology where sometimes it would repeat the same bus. So you take bus whatever to 23rd Street Station, you get off, then you get back on that bus, and you ride it around, and you get off, and then you get on the bus to the airport. And they could have checked, okay, make sure when you get off a bus, you get on a new bus, you're not getting on the same bus. Wouldn't make a lot of sense. They could have checked that. I'm not saying it would have proved correctness, but at least it would have ruled out an error that did occur. Another thing that would happen is that it might be that there's a bus that, for example, doesn't go to the airport as its final stop, and so it reports a route that doesn't include the airport as its final stop. So you make sure that in this trip, the starting point is the requested starting point, the end point is the requested end point, right? And it's supposed to find the best route. Well, maybe you go find one other route and you make sure this one is at least as good as that one. So it's not about proving that it is the correct answer. It's about ruling out classes of problems. And often by checking precondition and postcondition, we can do it. Now, when it comes to object-oriented systems, we'll be talking in a separate lecture about checking invariance and history properties. These are things that are basically true at any one time. History properties are things that are true between time A and time B, say T1 and T2, where T2 is later than T1. Sometimes you have a history property like it never goes down between those or what have you. Won't go into those now. Logical oversights, properties of data structures, that it should have no duplicates, it should have no null values within it. For example, it should never be empty. Yeah. Something about the internal consistency of the algorithm, that this counter is never decreasing or what have you. You check an efficient algorithm against a brute force algorithm. So their algorithm that they sweated over a lot, it used certain heuristics to try to get the best route. And the heuristics were designed to make it more efficient. And that's great. We all like efficiency in our algorithms. But what they were trying to avoid is a brute force algorithm, where it simply enumerates all possible combinations of schedules to get from A to B. And the problem is that sometimes their algorithm would not return the best solution. And they could have found it very easily by an assertion that would compare a brute force algorithm, which is very easy to write, just expensive, with the result from the efficient. Now you may ask, why would you do that? You're performing the brute force algorithm. Yes, during testing only. You won't be performing it on the user's side. And this will help give you confidence that your heuristic algorithm is actually working correctly. So when it comes time to ship to the client, we disable this assertion. And the answer is, ladies and gentlemen, you can disable assertions without changing the code base. That's the important point. Without changing the code base, without changing a line of code, you can disable the assertions in it. That's part of assertions, how they work. You can enable them and disable them, in many cases at runtime, but you can certainly do so without changing the code base just by the compiler flag. So you produce a version of your code for development. You have a brute force algorithm running to check the results of the clever algorithm. When it comes time to ship to user, comes time to deploy online, that assertion is disabled. It only runs during testing. Talked about a number of these, checking that a data structure, thing returned from an algorithm is not null. Results of, oh, this is a good thing, new code versus old code, refactored code. You're going to refactor code. Code will be crufty, and you refactor it. Does it do the same thing as the old code? You have the old code, you have the new code. Compare the results. Call them both. Get back results. See, are they the same? If they're not, that code ain't refactored. It's actually broken. You gotta update the new code so that it's a correct refactoring. And certain relationships assumed by algorithms hold. You folks know. I mean, I think everyone in here should have taken 360 before, right? When you're trying to most people maybe. When you're trying to demonstrate running times of algorithms, do a complexity analyses, even when you're dealing with data structures and reasoning about them, there's all sorts of clever realizations we have that this must be true at this point in the code, or this property holds. And we can check those things very easily in assertions. Okay? So important point here. Typically, a lot of our assertions are disabled in shipping code, in production code that's being used by the client. There's actually a philosophical disagreement about this. There's a segment of the community of developers who argue you should always keep assertions enabled, even on shipping code. And there's others that argue, no, in general, they should be disabled. They're only for testing. And there's some arguments in both ways I'm not going to get into. But one thing is clear. There may be certain assertions in certain modules that you want to disable because of performance, like they're performing a brute force version, and you want to disable those. Or others that would present arcane information to the user that would not be appreciated. Sometimes developers will actually put in code to handle the cases handled by exceptions, just in case it falls through. Really valuable to use logging in the context of assertions, so that if there's an assertion failure and you're engaging in debugging, you can go back to the log and figure out what was going on here. And certainly, make a habit of documenting your preconditions, postconditions, and assumed invariants, while you're writing the code. Terminating the code with an assertion. Unexpected termination. An assertion happens in user code during deployment or in deployed code for the client. What are some undesirable and desirable features? Well, undesirable is you drive away the user. They say this weird message came up. I have no idea what it means. Get it away from me. And sometimes there's some cost associated with that in terms of having to go deal with the user situation. On the other hand, sometimes it can be helpful to avoid corrupting data, provide some feedback if the need for someone to look at it, and to avoid a situation where you commit a transaction that shouldn't be. So I'm not going to take sides on this issue. I think there's several features to it. Now, a best practice here is you want all your assertions to be side effect free, to be pure, to have no side effects. Why is that? Why don't we want our assertions to have side effects in them?
So they're removed in production?
Yeah, they're removed in production. So it'll break the system if you remove them if it's counting on a side effect. So you certainly don't want to do this. Now, I've been around assertions for decades now, and assertions have evolved a lot. This is what we used to do back in the 80s and 90s for assertions in C. So typically there was an assert.h, part of the C standard library, as I recall. And what you would have is you'd have a function, that's an assertion function, and you would have a pound define of an assert macro. Folks know about C macro? No? You haven't seen C macros before? Oh gosh, I don't know whether to offer my condolences or congratulations. You haven't seen these before?
Yeah, we have
A few?
I have.
a bit of operating systems.
A bit? Okay. C macros, they're weird and potentially hazardous, but also useful things. Okay. So the idea is you do what's called pound define, and this basically says whenever I see an assert statement, something like assert something in there, substitute in this text here. So substitute in. And everywhere F appears, replace it with whatever. So if I say assert, foo, now it'll say if foo, do this, otherwise do that. And what's going on here more than that is taking advantage of a special feature of the preprocessor, to wit, here, if you have underbar file, it actually substitutes in as a string the name of the source code file that this is in which this appears, and the line number in which it appears. So the preprocessor, so before the C compiler ever sees your code, no pun intended, it actually performs a C preprocess. So it actually takes pound defines and expands them, strips out comments, and a bunch of other sort of minor things. It sort of goes through and does syntactic kind of manipulation on it. And one of the things it does is substitute this in, and these get placed in there at that stage. So this is the actual code that will occur. And basically this code is checking, is this condition true? If so, don't do anything. Otherwise, call this assertion function with this information.
So line is the line where F as an argument is?
Yes, correct. So this assert F will be in your code base, just like okay, it's not here, it'll be in the next slide, I think. You'll have an assert F in your code base, and this would be the line number that appears in your C file, and this would be the file name for that C file. It's a string, and this is an unsigned integer. Okay? And you'll notice what happens if debug is not defined. This pound define, this basically is saying, is debug on? Are we in debugging mode when we compile this? So it could be set by a compiler flag, or it could be set by a pound define elsewhere in another H file. But normally it'd be set by a compiler flag. So we say the GCC minus D cap D debug. Or we could say debug equals 1. So what will happen if debug is not defined?
An assert just does nothing.
It does nothing. If you see this, substitute in blank. Just
How do you terminate the code if it's false?
if it's false, it's going to call this assert, and this assert function, which is going to be called in some library. This assert function is going to say a bad thing happened at this file at this line number. Please speak to your technical support or something like that, or please investigate this. Typically, be for developers, it would say please, an error occurred of this sort, and then it would terminate the program. It will actually exit the program. It will bomb out of there. It will do an exit. We'll call exit of 1. So it will actually exit the C code, terminate, gone. Now, it might do other things. It might log it to a file. These days, it might send it over HTTP post to post it to a database of failures. But these days, typically, we would do something more sophisticated than that. We would actually record one more piece of information. What is that? What is that we record?
A statement about what the assertion is.
A statement, and actually 2 pieces, what the check was that failed. What was the nature of the check that failed? What were we checking? Was it that this thing is non-null? Or was it that the data structure contained no duplicate values, or what have you? Okay? So this is C code, and oh, here's the code, right? It flushes this as assertions failed at this place, and flushes, and here it calls abort. So this calls exit. It just bombs out of there. Boom, and it flushes third error so that you see this message. Dead. Program dies, but you're the wiser. Okay. This was from an example Chris Duchin used to give in 240. This is Newton-Raphson method for finding the root. Here, finding the approximate square root at a certain tolerance level. So here's the value of which you want to find the square root. Here's the tolerance, that sort of precision with which you want to find it. And here you might, to test it, you might be asserting, okay, that it's accurate to within a certain level. So here's the actual square root. Here's the one we're trying to take the square root of, and we want to make sure it lies within this level of tolerance. So here we're passing the tolerance to Newton-Raphson, and we're testing the result to make sure that indeed it is appropriate close. And here are some assertions that would fail, for example. Let's talk about the Java context. Here's some Java code. This is a index first if. So basically, we take in two arrays, and the idea here is we're trying to find the first index within those arrays at which they differ. These are arrays of ints, so we're going through each index to try to find the first index where the contents of the first array, rint1, is different from rint2. Okay, and you notice this is specification. It says, okay, they need to be at the same length, or they need to be both null. They can be both null, but one can't be null and the other not. And what does it return? The index, the first element in which the arrays differ, or -1 if no differences are found. Return code, right? And it modifies nothing. This is a statement you sometimes see. Rather than saying post condition, we break it up into returns and modifies. And this says that modifies neither. So you can either specify post conditions, which include both, or break it up into both of those. So here we assert, and note this is a C assertion, a Java assertion rather. We assert, okay, either both are null, or the lengths of the two arrays are the same. What is this colon? What's that colon do? Well, ladies and gentlemen, in contrast to C, we've learned something over these decades. In contrast to C, assertions are built into the language in Java. They're actually baked into the Java language. And assertion here is a special construct, and the first thing it takes is the condition, and then it takes a message, which is the message to indicate if it failed. And because it's a construct in the language, because it's built into the language, it has special powers. Now, those are in 470. We'll know this morning we talked about ways that you can have special powers, like use of laziness and so on. And that's not the power to sleep. But through non-strictness, you can do special things. But here in Java, we're stuck with the traditional world. And so because this is a construct in the Java language, it can know this is the condition for it and can print it out in the assertion message. And it knows where it is, line number and a file name. We don't have to pass it like we did for C. Have the C preprocessor pass it manually. The compiler could take care of that, and we have this nice little error message, and so this would be printed out if we want. Okay, corresponding C example would be something like this, where we assert this to be the case, and that goes to this assertion macro right there. Okay, here's another example. Normalize array. This takes in a double, and it takes in an integer. This is a count of elements. Okay, I said C. That's Java. It looks like I don't know, we could do that in C. So it takes in an array, and it takes in a count of elements in that array, and basically it is going to take the, it's going to return an array whose elements consist of the elements of the original array divided by the sum of those elements. So here, the preconditions are array, here array is, I should say, okay, so either array is null, or the count of elements is greater than 0, and the elements in array sum to greater than 0, i.e. the sum of them is greater than 0. And the return value is, if the array is not null, it returns a corresponding array with each of the elements being the original one, corresponding original one, divided by the sum. If the array is null, it returns null. Okay? And it modifies nothing. It doesn't change any aspect of program state. What does this modifies mean? It doesn't mean you can't assign to a variable in here. It doesn't modify anything that's externally visible. Everything that's modified lies within the code. There's nothing, it's not like the thing that we're passing in gets overwritten or something like that, or it updates some global state, some global variable. It doesn't do that at all, so we say it modifies nothing. There could still be things in the code here that are being modified, but they live only inside the function, so they're not externally visible. Okay, so here we check if it's null, and so we return null. Otherwise, before we go and we do our work, we assert that the count of elements is greater than 0, because either this has to occur or that has to occur. And we assert that the minimum element of the array, for example, is greater than or equal to 0. And we might also assert that the sum, once we compute it, is greater than 0. Just checking the precondition. Yeah?
So like a array min, that's like a function that's defined like specifically for the assertion, right?
Yeah, that's right.
So like what would be best practice for like where you put it in your code?
The array min?
Yeah.
I would put it basically in the same module or same code base that this is used, but it will probably be a private method, and it will be used for that. But this gets into, remember I talked about earlier, testability, and the idea that sometimes to help your program be tested, and I would include in here writing assertions as part of that, we create extra code that will do things that isn't otherwise required, and array min would be an example. So I would put it together with this, but make it private, and that's part of the scaffolding. Just like when we build a building, we have to build, we have to often put scaffolding to sort of allow workers to get access to it. We put temporary structures on it. So it is with programs. We're going to be creating this code and just keeping it with this code, and it will be used internally by this code as part of its error checking. Does that make sense? Yeah. Other questions? Okay. So I wouldn't, put it off in a totally separate case. Okay, here's another one. Identify index. Okay. Here we go. Here we have an int array, and we want to, and it's of a certain length given by count elements. Why are we passing this around with this int array in C?
Because it doesn't have like a length property.
Yeah. See, we don't even have a length. We don't even have a stinking length. So we got to pass it around separately. I know. I think it's not too much better than like hitting rocks together. Trying to scrape things with them and trying to make sparks. Yeah, so we had kind of a threadbare existence in some ways back then. So here's the array, but we can't, in Java, we can't say, okay, what is the length, or in C, we can't say what's the length is directly, so we pass around a bit of extra information. And by the way, if these two are off, bad news can happen. What can happen if those two are off?
We might go past the end.
Yeah, we might go past the end. Like if we say it's of length 10, and it's actually of length 8, we might go past the end, and then all bets are off, because we might be writing on top of other data structures. Suddenly you've overridden your red-black tree. Or maybe you're writing on code. That gets really exciting. you start writing on the code base, and then you start executing your data. Bill Gates was really good at that back in the day. And so you sometimes you want to be very careful about making sure these are consistent. So this takes an array. It consists of an array and then a length of that array, and then we have a value to match in that array, the value for which we're looking. And the idea here is we're going to look in this array for the first place that it matches this value, and if we can't find it at all, we'll return -1. Otherwise, we'll return the index, which is 0 or more. That's why -1 is distinguished, right? So here we're going to assert that that's not equal to null, that this array we passed in. Assert that count elements is greater than or equal to 0, because if we passed in something that was less than 0, that would be pretty whacked out, saying we have a negative length array. Then we're going to be searching to see if at the end if we could match that. In terms of post conditions, I mean, you could test here, for example. What could you test in terms of a post condition? Here, what would be an obvious thing, or not so obvious thing to check in terms of a post condition? For the value that's returned, it's supposed to return an index. So what can we check? The value that's returned should either be what? -1, the distinguished value, or it should be 0 or more. But it should never be something like -2. That doesn't make sense. More than that, if it's -1, at least on the face of it, the first element of the array shouldn't be equal to that. Then it'd be 0, right? So we could actually do some spot checking just to make sure it's not something really, really buggy. So we could check that. But at least you want to check the return value is either -1 or it's greater than or equal to 0. Another thing you could do, what else could you check here really quickly as a post condition?
If it's not greater than count elements.
Okay, good. It's not greater than count elements. Excellent. That's excellent. Bingo. That's great. But I'm thinking about one other thing. Ladies and gentlemen, there's some times in life where our programming job hands us a good set of cards. If I'm testing a square root operator like that Newton-Raphson, one thing I can do is, it's hard to find a square root of a number. It's fairly hard. It involves a lot of steps, but it's really quick to check if it's a square root once you give it to me. Why is that?
It has an inverse function.
Yeah, it is an inverse function. So I can, if you give me what the putative square root, the thing you claim is the square root, what can I do? I can square it, compare it to the original value. Given the answer, I can quickly check, verify. Is that something I could do here? This is supposed to find the first element in the array where this value occurs. What could I do at least? It might not show that it's perfect, but what could I do in checking the post condition?
You could check that index in the array.
Yeah. Yeah, that it matches. So if it's found a putative index at which to match appears, I could at least check at that index, does the contents of the array equal to match? If it doesn't, something's broken. And you may say, oh, come on, the code couldn't be that broken. Think back, ladies and gentlemen. If your code is anything like mine, sometimes it's really broken. And it's not just the first time you write it. Sometimes you got to tweak something in it, you're debugging, you're trying to fix something quickly, some other code it depends on has changed, and it can break the code. So why not check it? It's easy to check. Now checking it's the first one, well, that would require some more work. But at least you could check that the index of the thing the index that we're returning, if it's not -1, if it's a legitimate index, that at least it's within bounds, as was said earlier, and that the value there at least matches what we're searching for. Does it mean it's perfect? No. Does it mean it rules out whole classes of errors? Yeah. It could rule out whole types of errors, whole classes of errors that could occur. So why not check it? It's so easy to do with an assertion. And that's what I'm going to say when I look at your code. So easy to do. So I expect to see lots of assertions. Okay, so I'd mentioned these things can be enabled and disabled at runtime. And with Java, I noted that the assertions are built into the language. So you could do minus enable assertions, minus disable assertions, to enable assertions and disable them. You can also, and this got messed up formatting wise, you can also enable them at runtime or disable them at runtime using a tool called reflection. How many people in here have used reflection in your programs before? A couple people. So you could do it to like to figure out like when code's loaded dynamically at runtime to get a reference to an instance in that code that matches some interface, or you can use it to call a function whose name is only a string now, and you want to call the function with this name, pass it certain parameters. Reflection is a neat technology within Java and many modern languages. And we can enable and disable assertions within our code base using that, but we can also enable them from the compiler. So we can enable assertions within a certain module of our code. Good stuff. By the way, this is by a really good book in the Java programming language. There's another one, Effective Java, that I'd strongly recommend. So assertions, enable and disable. Now, in more modern languages yet, like Scala, this is taken to a yet higher level, and we have awesome capabilities to do assertion checks, to do ensures. We can actually write ensures in a special way at the end of a bit of code that will actually check the post condition when it's leaving. It's great stuff, and it helps us do even more easy checking. Replace here we have ladies and gentlemen, an existing value in some data structure called values, and that's a data structure that may be a field in the surrounding class, and we have a new value we want to use to replace that old value. So here we iterate through, this is Java, we could just ask values.length. We see if we can find the value, and if so, we assign that index to the new value, so we overwrite that old value. And this should always be present. This value for which we're looking should always be present. That's a precondition. And so we can check legitimately if we've reached this place, what has happened? So if we've reached this place here, what's happened?
You didn't find the value?
Didn't find it. It fell through here. It went through each of the values and it never found it. If it found it, it would have returned by now. If it got here, it didn't find it. So we can say assert false. And this is a common thing. You say, okay, if I'm here, bad news. Assert false, and we give a message that says this, right? So that the person who sees that can see it. This might go to log messages. Okay, what's wrong with this code? This was from Steve McGuire's book, one of the early books that described assertions, as I recall. Steve was a colleague of mine when I was on the Excel team, amongst other things, although he was in a different team. So this is a str_dup utility. So this basically duplicates this string and returns a new string that's a duplicate of it as allocated with malloc. What's wrong with this code? What's wrong with this code? Well, I tell you, it's using assertions in the wrong way. It's using assertions in a way they shouldn't be used. What is it doing? Where's the assertion here? Well, it's two places. This assertion at the top, is this okay? Yeah, it's checking the precondition. As long as it's really have a comment up here. It's part of its assumptions, its preconditions. That str is non-null.
Oh, I was just going to say the second one checks for like your memory if it was successfully allocated.
Yeah.
That's not something you can
control.
That's not something you can control. Assertions, ladies and gentlemen, are about programmer errors. They're about the things we can control. Through our carefulness of our reasoning and coordination with each other, we can make sure that an error, doesn't happen, the preconditions are violated, or that the postconditions work properly given the preconditions. That's under our control. This is not something we can dictate to the world. There shall not be any out-of-memory exceptions. That's not acceptable to say memory is always available. That's not something that is going to be acceptable for real-life code. So this is an abuse of assertions. This is using assertions as if they are an exception handler or something like that, with no recourse. So that's not something you want to do. So you want to instead handle this. Okay? I have to cut off now, just as you might glimpse beauty. But that beauty will be reserved for those in 470. How to handle these in a much more beautiful level, in a much more robust level, a way that's scalable, a way that's effective and reasonably high performance, avoids a lot of the problems. But use assertions, ladies and gentlemen. Please use them early, please use them often, use them throughout your code bases. Thank you very much.